Hello. Today, we're learning part one of the fundamental theorem of calculus. So this is going to relate with the part two that you've already learned. So just try to remember, what did that say? It says if you want to figure out this definite integral of little f over the interval ab, what you need to do is find this antiderivative, capital F, and evaluate it at the two endpoints and subtract. And this antiderivative really came out of nowhere. So what we're doing today is trying to see where that came from in a way. And also recall that if you have a function, so big F, just by itself, then this right-hand side, f of b minus f of a, is the net change of f over that interval. So in the example where little f is velocity, then big F would be position, and your final position minus your initial position is your displacement. So that's why it's sort of net change. It's just final minus initial. And what the part two says is that in order to find the net change of big F, we need to integrate the rate of change. So from the perspective of big F, it's like I want to know what is the net change, f of b minus f of a. What I should do is integrate big F prime over that interval from a to b. So to find net change, you integrate the rate of change. So what we're going to need to understand the part one theorem is the concept of an accumulation function. So this is where we have a function. So this whole thing is the function. And the independent variable for this function is x, which only occurs right here in the upper limit of integration. So what this function does is when I give you an x, it says to integrate from our initial constant a until we get to the input x. It's really best to understand this with a picture. So here, big F of x is going to be the integral from 5 until x of f of t dt. So here we're thinking of this as the t axis, and this blue function is little f of t. And then what's drawn on the left, this area here, this would be capital F of 10. Right, so the area there is the integral. This area here is the integral from 5 to 10 of f of t dt. And then this integral here, this is the integral from 5. This area here is the integral from 5 until 10, 11, 12, 13. Right, so this right-hand area that's drawn is big F of 13. So R is starting in the same place, which is just some chosen constant, and integrating until you get to x. Okay, so this is the theorem in this box here. Suppose little f is continuous over the closed interval ab. The accumulation function, big F of x, is an antiderivative of little f. So the derivative of the integral of f at the point x is exactly f of x. So this is a deep connection between differentiation and integration that says in the correct interpretation that they're inverse operations of each other. You take you start with f, take its integral, then take its derivative, and they cancel out in a way. Very precise way, but they do. So the way that I make sense of this is to remember that this accumulation function, as x increases, it means you're picking up more and more area. And then the derivative of that is the rate of change at which we're picking up more area. And so then we're taking our rate of change at a particular point x and saying that it's exactly equal to the height that the function is at that x, which is f of x. So if the function suddenly became constant at that x, and were to stay that for an increase of 1 along the x-axis, we would add a little rectangle of area f of x times 1, which is just f of x. So that's the rate of change. So here's a picture of that. Here's my f of t. It's the same one as before. We're integrating from 5 until x. And then the rate of change at exactly 10 right here is equal to f of 10, right? So this value here is f of 10. And that's exactly the rate of change that we're picking up area. So if you're coming along and all of a sudden it were to get constant, right? You'd add this rectangle of area exactly f of x, if this was 1 unit here. So the rate of change at a single point here is exactly the height that you're at, which does make sense. Anyhow, what sorts of problems can we ask you to do with this? So here's an accumulation function, capital F. So just to get our bearings, first we're going to calculate what is capital F of 4. So that means it's the integral from -2 to 4 of t squared minus t plus 1 dt. By the way, the reason we have to use t is called a dummy variable here. It's just we couldn't have x's and t's all over the place. That wouldn't make sense. So we need to use the t because the variable for the actual big F is just that one constant there. So we find our antiderivative. This is using the FTC2. You all should know how to do this by now. So this is kind of review. And the point of me including this is just that big F evaluated at 4 is just the value of a definite integral. It's our signed area. And here's another example, big F of -2. That would be the integral from -2 to -2 of this function, which of course we don't have to calculate because we remember integrating over a single point is always 0. Okay, so this is just getting our handle to understand accumulation functions. Here's a more typical problem. So you're given an accumulation function of sorts, except instead of just an x here, there's an x squared, just to make it tricky. So it says compute g prime of x and then evaluate that to get g prime of 2. So what I like to say is that the FTC theorem we learned, it doesn't work when there's an x squared up there. It's very particular. It only works when there's an x up in the upper limit there. So define big F of x, where I just replace the x squared with x, because that I can use the theorem. So FTC1 tells me that big F prime of x is exactly square root of x times e to the x. It's the height where we're at. And now understand this g function we're given in terms of the capital F that we know how to take its derivative. And so how do I get this from this? Well, if I plug x squared in for that x, I get that. So big G of x is big F of x squared. And now I can figure out G prime of x in terms of F prime. This is going to be F prime of x squared times 2x by the chain rule. Okay, and then I know what big F prime of x is. So big F prime of x squared is square root of x squared e to the x squared, which is x e to the x squared. So here I get x e to the x squared times 2x, or if you want, that's 2x squared e to the x squared for our final answer. And then to find g prime of 2, I would just plug in 2. So that's going to be 2 times 4 is 8 e to the 2 squared. So 8 e to the 4. All right, now here's your try it yourself problem. This one's like a little easier than the one we just did because you just have a 2x here. So you're still going to have to go through the same steps, but it's not so bad. So compute h prime of x and then h prime of 3. And by the way, both this function here and this function here are functions that don't have closed form antiderivatives, so you can just write down. So you really can't do this by trying to use FTC2 and then take its derivative. You really have to, like, what function's in derivative is square root x e to the x? I don't know. Nobody knows. Try plugging it into like Wolfram alpha, you'll get something crazy. So you really have to understand this theorem to do this. And here is the answer. And your teacher may go through the relationship between FTC 1 and 2 in class with you. We're not going to do that right now, but once you know FTC 1, it's super easy to write down why FTC 2 works. The hard part is saying that this is an antiderivative of any continuous function. Okay, so it might be hard to find them, but at least abstractly we know they exist. Great. I hope you enjoyed that, and see you next time.